Yeah, I'm in the process of buying a house this morning, so it's a little complicated. But also, I've noticed this morning that, and unfortunately, it's too late to fix it. There is a problem with the file, and you will see the theorems and definitions are not showing properly, but we'll see. Okay. Um, these are some references. Most of the work is joint with one of my former PhD students, Hong Lu, and some of the work is also joint with one of my frequent collaborators, Michel van Frankenhausen. And normally in the theorems, it's mentioned which reference it's alluding to, but unfortunately, you will not be able to see that in this particular file because it's hidden for some reason. Okay, so there were papers in a special issue of fixed point theory and application dedicated to Arnold, to his jubilee, and papers in p-Adic number, ultrametric analysis and applications. A long survey article with Hong Lu in contemporary mathematics. And then papers joint with Michel van Frankenhausen again, well, in contemporary math as well. And more recently in fractal and fractionals, as well as, although I will not talk about this particular topic, in p-Adic numbers, ultrametric analysis and application, it's under, it's in press now. It's no longer under review, it's in press. Okay, now the general references explaining the theory of complex dimension, not in the context of p-Adic analysis, but in context of either Euclidean analysis or metric spaces, is provided in many books and papers of mine and with various collaborators, but especially in those two books. So Fractal Geometry, Complex Dimension and Zeta Functions, Geometry and Spectra of Fractal Strings, which appeared in the 2013, the second edition appeared in 2013, the first edition appeared in 2006 with Springer in Springer Monographs in Mathematics. And the second book, so this is about the theory of fractal strings in Euclidean space, in the real line here, really. But the higher dimensional theory of complex dimension has been developed fully in a series of 10 papers with these two co-authors, Goran Radunovic and Darko Zubrinic. And in a book called Fractal Zeta Functions and Fractal Drums, Higher Dimension Theory of Complex Dimensions, which appeared also in Springer Monographs in Mathematics with Springer in 2017. It's about 700 pages long. Okay. So, all right, so this is for the background. Now, for the references. And so let's talk about the plan. The plan of the talk is the following. So we'll give a brief introduction, although I think it's probably not necessary for this audience, but on p-Adic numbers. Then talk about p-Adic fractal string, which is probably necessary for this audience. And at least I will introduce in the first part the notation that I will use to discuss fractal strings, p-Adic fractal string. We'll discuss the important example, a motivating example of the Cantor string, the 3-Adic Cantor string, and which is not the same as the ternary Cantor string. And then discuss the notion of geometric zeta function and their poles, which are called the complex dimensions. Then we'll introduce the explicit tube formulas in the context of p-Adic geometry, p-Adic analysis. And these are called fractal tube formulas in this context. And you could call them p-Adic fractal tube formulas here. And as a preliminary, we'll discuss the notion of inner tube and its volume, which in the case of p-Adic geometry is a little more delicate than in the Archimedean case. And then if time allows, and please, Mr. Chairman, let me know when I should stop. Should I stop at 2:50 or?
Yeah, so the plan generally is 50 minutes past the hour and then 10 minutes for questions. You did
Okay.
start a couple minutes late, so if you go a couple minutes past 50.
That's fine. Thank you. But please don't, please interrupt me anytime and let me know that the time is over. And also anybody who wants to ask question is welcome to ask question anytime, please. So if time allows, we'll discuss the more general context of p-Adic self-similar string. I mean, more general than the example of the Cantor string, which I will have stressed by then. And we'll discuss the structure of the complex dimensions and the corresponding fractal tube formulas. And okay, in the also the notion of average Minkowski content, and go back to the Archimedean Cantor string, the non-Archimedean Cantor string. All right. So as an overview, because it may help to understand at least good part of the talk until I go into the details of the case of self-similar strings. Let me mention that p-Adic fractal strings are going to be defined as bounded open subset of QP, the p-Adic real line. I mean, real, quote unquote. I mean, the non-Archimedean analog of the real line, I should say. And so these will be bounded open subset of QP, and as such, there will be union of intervals of QP, and we'll see what that means. These are just scaled and translated copies of ZP. And then we'll talk about p-Adic self-similar fractal strings. Well, not immediately, but p-Adic self-similar fractal string will be an important example of those. Among them, the p-Adic Cantor string. There is associated to any p-Adic fractal string a notion of geometric zeta function. So it's a certain meromorphic function, will turn out to be meromorphic in the whole complex plane in this case. It's a function of a complex variable, and it's complex value. And after a suitable change of variable, which is intimately connected to P, the underlying value of P, of the prime, it becomes a rational function. So therefore, the zeros and the poles of the geometric zeta function will be periodically distributed along finitely many vertical lines, and they will have the same, what I call oscillatory period vertically. So they will be periodically distributed along vertical line, and the period will be the same on each vertical line. The poles of the geometric zeta function are by definition the complex dimensions. And since the function is defined in the whole complex plane, there is no ambiguity about what is meant here. And so the goal is to describe the oscillations in the geometry. I'm sorry, okay, let me go back 1 second. I'm saying the poles are the complex dimensions. That's true. The geometric zeta function in the case of p-Adic self-similar string, which is an important case of fractal strings, are always meromorphic in the whole complex plane. In general, in the general case of a p-Adic fractal string, it may or may not be meromorphically continued, and then you have to be a little more precise about what you mean by poles. There is a notion of visible pole, which I don't want to go into in the talk unless there are questions about that, and I'll be glad to explain more precisely what that means. But there is a suitable notion. Roughly speaking, you talk about visible pole within a given open set or connected open set to which the zeta function can be meromorphically continued. And so the goal here of the theory of complex dimensions, both in the Archimedean and the non-Archimedean case, is to describe the oscillations in the geometry of your fractal object, in this case, the p-Adic fractal string, via, for example, fractal tube formulas, which are expressed explicitly in terms of the complex dimensions. And in particular, fractals in the theory of complex dimensions that I've developed are defined so fractals are defined as geometric objects which have at least one non-real complex dimensions. In the case of, for example, self-similar, p-Adic self-similar fractal string, they will have infinitely many complex dimensions, and in particular, non-real complex dimensions. So they will be fractal in that sense. And in fact, any object that has been called fractal in the past is fractal in this sense. And many objects which were thought to be fractal, either in the Archimedean case or non-Archimedean case, but especially in the Archimedean case in Euclidean geometry, but which were considered as borderline because, for instance, the Mandelbrot definitions did not apply to them, are fractal in the sense of the theory of complex dimensions. Let me give you an example. In Euclidean case, if you could consider the Cantor curve, which is this famous curve, or the Devil's staircase as it's called in fractal geometry, that is this curve that is monotonically increasing from 0 to 1 and is is piecewise constant on the complementary intervals of the Cantor set, that is on the intervals that you obtain by constructing the Cantor set, the usual Cantor set, the ternary Cantor set in the real line. So this curve is not fractal in the sense of Mandelbrot because its Hausdorff dimension is equal to its topological dimension. They're both equal to 1. But it turns out that it is fractal in the sense of complex dimension because it has complex dimensions which are not real. In fact, it has infinitely many, which are the dimension of the Cantor set, the complex dimension of the Cantor set, namely log 2 over log 3 plus 2i n pi over log 3, where n is any positive, negative, or 0 integer. Okay, so after these preliminaries, let me go into this. So I mentioned the collaborators, Hong Lu or Tim Lu, and for part of the work, also Michel van Tronkenhausen. Okay, and I've mentioned this book already, the Fractal Geometry Complex Dimension and Zeta Function, which gives a theory of complex dimension in the case of real fractal string, in the real line. All right, so as we know, every Ostrovsky theorem says that every non-trivial absolute value on Q, on the field of rational numbers, is either equivalent to the usual absolute value of the rational numbers or the p-Adic absolute value for some prime p. And of course, we know how to define the p-Adic absolute value. It's recalled here, but maybe I shouldn't spend too much time on that. Major difference between the two, the standard absolute value on the rationals and the p-Adic absolute value, is that one just satisfies the ordinary triangle inequality, whereas the second one satisfies a stronger form of the triangle inequality, which is that the absolute value, the p-Adic absolute value of the sum of two numbers is less than the maximum of the p-Adic absolute value of each of these numbers. And this has many, many consequences, as most of you, all of you, I'm sure, know. All right, so Ostrovsky theorem says that there are two kinds of absolute values, of metric completions of Q. That's one way to state the Ostrovsky theorem. The first one is the usual absolute value on the rational number, and that gives rise, the completion gives rise to the real numbers. That's the Archimedean case. And the non-Archimedean case, for any prime p, you obtain the, after completion of the p-Adic absolute value on the rationals, you obtain QP, the field of rational numbers. So these are all the field metric, the admissible field metric completions of Q, and up to a trivial equivalence relation. And of course, in general, one writes R equals Q infinity to stress the fact that in some way this corresponds to the prime at infinity. But of course, much of the mystery of number theory, I would say, lies in the huge difference between the Archimedean and non-Archimedean case in the case of the rationals, and the huge difference between the reals and the p-Adics, even though one can somewhat artificially put together the two notions, so the two completions inside the Adels, but the ring of Adels, which is a beautiful construction, but still does not put on the same level the reals and the rational. There's been beautiful work to try to bridge the gaps between the Archimedean and non-Archimedean case, but I think we are still not fully understanding what are the true connections between the two cases. In my opinion, the Riemann hypothesis may not be solved until we fully understand this, how to merge the two. Okay, and part of the theory here is also aimed at trying to find methods that will work both in the Archimedean and non-Archimedean case in the theory, within the context of the theory of complex dimensions. And we did find such methods. Okay, so in the Archimedean case, as you know, the absolute value of the sum of two numbers, for example, is larger than the absolute value of the number. And in the non-Archimedean case, is less than the sum of the number, which is somewhat surprising and implies in particular that the p-Adic, the ring of p-Adic integers, is a ring, truly, which is absolutely not the case in the Archimedean case, because, for example, the interval -1, 1 is not stable under addition, obviously. So we have already huge algebraic differences, and one can see throughout the theory of complex dimensions of p-Adic strings, the difference, the consequences of these differences as well. Okay, so as we know, QP can be written as the set of Lorentz series in P. And the unit ball of QP, or the field of rational numbers, is equal to the, by definition, it's just the set of rational numbers with p-Adic absolute value less than 1, less than or equal to 1, and is just given by the set of power series in P, that is starting at A0 times 1. And this is a ring, as I just mentioned, because of the ultrametricity of the field of p-Adic numbers. Now, a property that it may not be as familiar to most of you is the self-similarity of ZP, although I'm sure you know it, but you've seen it, and it will play an important role here. So ZP can be written as, in an obvious manner, as the union of the translate of C, translate by C of PZP. So you multiply ZP, you scale it by P, the prime, the underlying prime, and you take the union from 0 to P minus 1. That's clear here in this definition of or this property of ZP, because you can choose any starting point here. A0, any A0 if you wish. So this self-similarity is a key here. All right. As I say, there is this glitch, and I don't know, I just realized it this morning with the file. It wasn't a problem before, but it just appeared. I'm not sure what happened. So I apologize for it. So you will not see, so this is a definition, but you will not see the difference between definition and theorem, so I will mention it orally. So a p-Adic fractal string is, so we'll call it L sub P, so P is a fixed prime from now on, is a non-trivial bounded open set in the p-Adic field, QP. So we'll call that set omega. All right. Now, we can also write LP as a union of balls, after simple reasoning, one can see that you can write it as translates of scale copies of ZP. So the scale copy is p to the nj, the scaling. Nj is some integer. And aj is any p-Adic number. So of course, the aj is somewhat arbitrary because the center of a ball, as you know, in a p-Adics can be chosen anywhere inside the ball. So, and you take the union from j equals 0 to infinity. All right, so this is what concretely a p-Adic fractal string is. And we'll see that there are a number, because of this arbitrariness, I mean, somewhat arbitrariness of the choice of aj, for given p-Adic string, there may be many ways of writing it, but the theory will not depend on that. That is, the complex dimensions in particular will not depend on this choice, and the geometric zeta function prior to that will not depend on this choice. Okay, QP is locally compact, so as we know, there is a unique, and it's a group, additive group. So in particular, so it's there is a unique normalized probability measure on QP. I mean, probability measure. It's a probability measure on ZP, but it's a unique positive measure, and it's on QP, and it's normalized so that the Haar measure of ZP, the unit ball, is equal to 1. So in particular, it has this property that the Haar measure, so I'll denote it by mu sub h, because it's also the Hausdorff measure, the one-dimensional Hausdorff measure of QP, turns out. So QP is one-dimensional from point of view of Hausdorff dimension, of Hausdorff measure. So mu h of a plus p to the n zp is p to the minus n for any n in z, z being the set of integers, the usual set of non-negative, negative, or 0 integers. And again, a plus p to the n zp is simply the ball of center a and radius p to the minus n in QP, equipped with its usual p-Adic absolute value. Okay, so I'm in here a non-trivial. I'm excluding the case when you have a finite number, a finite union of such balls, disjoint union of such balls. This is disjoint union, by the way, because this case is, I mean, it's admissible, but it's not very interesting. So to avoid exceptions to, I mean, obvious exception and complications in the statement of theorems, I'm just going to assume I have a countable union of such, countably infinite union of such balls, of unions of such balls. Okay, so that's what a p-Adic fractal string is. Now we can define the geometric zeta function of LP. It's just the sum of the Haar measures of these balls, or these p-Adic intervals, if you prefer to call them that way. And if you remember, the measure of this ball is p to the minus nj. So when we raise to the power s, yes, I forgot to say, it's the sum of the measures raised to the power s. S is a complex number, suitable complex number. And so this is just the sum of p to the minus njs. And here, s is a complex number with real part large enough, let's say. But it will turn out that the best bound, lower bound for real part of S is the so-called Minkowski dimension. And I'll define it a little later of the string LP. But let's just say real part of S greater than 1 would be enough, because it turns out that the Minkowski dimension is less than 1 always, less than or equal to 1. Now the complex dimensions of LP are relative to some window W. I don't want to be too technical, but it's the set of poles in that window that are, the set of poles of zeta LP, which lie in this window. So what is a window? It's a suitable closed subset of C containing a screen. Okay, I don't want to go too much in detail. Let's just assume that W is replaced by a connected open set of QP, of the complex plane, I'm sorry, W, let's replace it by a connected open set of QP. I'm sorry, doing too many things right now, selling a house, buying a house. Okay, so it's a set of complex numbers that belongs to a given connected open set to which the zeta function can be meromorphically continued. So let's just take a connected open set to which zeta LP can be meromorphically continued. Let's assume there is such an open set. Otherwise, the theory is not very interesting. And let's look at all the poles belonging to that connected open set. These are the visible complex dimensions. In many cases, for example, for self-similar strings, p-Adic self-similar string, we'll have continuation to the whole complex plane, and in which case you don't have any ambiguity. But for the general theory, you have to be a little more precise. And I prefer not to go into the notion of window, screen, and etc., which are essential to precisely define all the theorems, but I just want to give the idea, not go into the details. You can find all the details in the papers if you're interested. By the way, in the book, Fractal Geometry Complex Dimension and Zeta Function, there is a special section, a long section, at the end in the last chapter, chapter 13, on the case of p-Adic fractal strings. So you can find many, if not all, of the results I'm talking about there, and explain in a way that that is reader friendly, even for somebody who doesn't know too much about p-Adic analysis. Okay, so what is the Minkowski dimension? So this is another definition. So one way to define it for LP, this is the inf of the non-negative real numbers, such that the volume of an epsilon neighborhood, that's something I will define more precisely later, of the string is bounded by a constant times epsilon to the 1 minus alpha. So it's bigger of epsilon to 1 minus alpha as epsilon tends to 0. So it says that this volume of the epsilon neighborhood, so the set of points which are within a distance less than epsilon from your open set omega, defining your fractal string. So the volume of that epsilon neighborhood, that's VLP of epsilon. It will be a little bit more precise than that later. I will explain, because in the p-Adic case, you have to be careful, very careful, in fact. But let's just leave it at that. It's the set of, so it's the volume of the set of points within a distance less than epsilon from LP, from your open set defining, bounded open set defining the fractal string. Okay, so this defines D, and there is a unique number defined by that quantity. It's also the sup for which this quantity divided by epsilon to the 1 minus alpha has a lim sup equal to infinity, for instance. And this inf for which this lim sup is equal to 0. So all these notions are the same and define the Minkowski dimension. It's technically the upper Minkowski dimension, but I don't want to be too technical. Okay, so now that's a theorem. It's not a definition, the next statement. Let LP be a non-trivial p-Adic fractal string, and that's the main reason why to assume it was non-trivial. Then D is equal to sigma, the abscissa of convergence of zeta LP. So if you remember, zeta LP was defined by this Dirichlet series. It's called Dirichlet series in number theory, and in analytic number theory. So it has an abscissa of convergence, which I will recall in a second. And the basic theorem here, the first theorem, is that D equals sigma. It's not obvious at all. I had proved such a theorem much earlier in the case of real fractal string. In the case of p-Adic fractal string, the proof is a little trickier, but we have now, I mean, a few years ago, found a unified proof that works both in the real and I mean, in the Archimedean and non-Archimedean cases, that is the real and the p-Adic case. In case of real p-Adics, real fractal string meaning bounded open subset of the real line, and p-Adic fractal string that is bounded open subset of the p-Adic line of QP. Okay, so what is the abscissa of convergence? So if Lj, your sequence of lengths, in our case, it would be p to the minus nj, the sequence of lengths with the previous notation. Then sigma is the infimum of the alpha, such that the sum of Lj to the alpha is infinity, is less than infinity. So it's also the set, it's the infimum of the real part of the complex numbers for which the Dirichlet series defining the geometric zeta function is absolutely convergent. It's equivalent. It has to be proved, but it's known in the theory of Dirichlet series. And so you can apply it in this case. So it's again also the infimum of the real part of S, such that the Dirichlet series, sum p to the minus nj times S, defining the geometric zeta function, is absolutely convergent. Okay, it follows from this, from the previous theorem, that d, the Minkowski dimension, is always between 0 and 1 for a p-Adic fractal string, and it's equal to sigma, the abscissa of convergence. So it also follows that the zeta function is meromorphic to the right of d. I mean, holomorphic, I mean, to the right of d. So for real part of S strictly greater than d, the series is convergent, the Dirichlet series defining the geometric zeta function, and defines a holomorphic function. So it doesn't have any poles. That means there are no complex dimension to the right of d. And strictly to the right, there could be complex dimension, and in fact, in general, there are. I mean, not always, but certainly there are. On the line real part of S equals d, I mean, beside d itself, d will typically be a pole as well. It will always be a singularity, but it will be a pole in general, often. And so it will be a complex dimension, but there might be other complex dimension on the vertical line real part of S equals d. It will turn out that these determine the leading oscillation, geometric oscillations of your fractal string, p-Adic fractal string in this case. And that's one of the key meanings of a complex dimension. They tell you precisely about the intrinsic oscillations of these fractal geometry, like our non-Archimedean geometries, and the leading, the oscillations of leading order will come from D, the real part. So just to tell you, these you can think of complex dimensions as giving you information about geometric waves traveling your fractal geometry. In this case, your non-Archimedean geometry, your fractal string. And so these geometric waves have amplitudes, have amplitudes and frequencies. The amplitudes are intimately connected via the explicit formulas that I will mention, the fractal cube formulas, for example. So they are intimately connected, the amplitude, to the real part of the complex dimension. The larger the real part, the larger the amplitude. And that's why D, the largest possible real complex dimension, is determining the leading oscillations of the underlying geometry. Whereas smaller values of real parts of complex dimension will give you amplitudes of lower value of lower amplitudes, and therefore oscillations of lesser order. Now, the frequencies of these geometric waves are telling you directly the frequencies of oscillations, the frequencies of the geometric waves. So real parts of complex dimensions are directly connected to the amplitude of oscillations. Imaginary part of complex dimensions are intimately connected to the oscillate, to the frequencies of the oscillations. Okay. Now let's talk about the triadic Cantor string, which we introduced with Tim Lu in this paper dedicated to Vladimir Arnold's jubilee. All right, so you have it here. So you have Z3, so P equals 3 here. But maybe it's better to look at the graph. So if you look at the graph here, you have the usual construction of, think of the usual construction of the ternary Cantor set in the real line in the interval 0, 1. You remove the middle third interval. So here, the analog of the middle third interval is going to be 1 plus 3 Z3. So we remove this one. Oh, I'm sorry. We remove this one in the construction of the Cantor set, the usual Cantor set. And here in the construction of the triadic Cantor set, instead of Cantor string, we would remove this middle third. Now the Cantor string is what is the union of all the deleted middle intervals. So if we call these middle intervals, these are triadic intervals. So this, at the first stage of the construction, we are deleting this one. So we are keeping, to construct the triadic Cantor set, but for the Cantor string, we are keeping it. We are keeping this one. So this is this first one here. Now, at the next stage, the middle thirds are here and here. So we keep them for the Cantor string. We delete them for the Cantor set, triadic Cantor set, triadic Cantor string. So that's why we have kept them here. So we have 3 plus 9Z3 and 5 plus 9Z3. And then at the next stage, you'll have 4 triadic intervals of lesser lengths, etc., etc. And you keep them at each stage to construct the triadic Cantor string. You delete them to construct the triadic Cantor set. So the non-Archimedean or triadic Cantor set, C3, is the intersection of those intervals that you would keep after having deleted the middle thirds. So this would be, for example, 0 plus 3Z3, 2 union 2 plus 3Z3, union 0 plus 9Z3, union 6 plus 9Z3, and so on, union 8 plus 9Z3, etc. So this would be T1, T2, and you take the intersection of these, and this is exactly the Cantor set, the triadic Cantor set. Now you can construct analog of this triadic Cantor set for various P's, and we've done that in the more recent paper with Michel, which is in press, and Tim, but I'm not going to talk about that here. Okay, so CS3, the triadic Cantor string, is the disjoint union of these deleted middle intervals. And the triadic Cantor set is the complement of CS3 and Z3. So this is what is left after having deleted the middle third intervals. And it is a compact subset of Z3, of course. It's a closed subset, but it's compact. And it's given here, as I mentioned earlier. Now, it turns out that this triadic Cantor set is a self-similar set in a precise sense, which I will explain at the end if I have time. It's a self-similar subset of Q3. Okay, now the Cantor string, the triadic Cantor string, as geometric zeta function, of course, it's a p-Adic. It's a triadic fractal string. And so zeta of that, the geometric zeta function is given by this. Since we have at each stage of the construction, we have 3 to the k intervals of multiplicity to the k minus 1. Since we had like 1 at the first stage of the construction, 2 at the next stage, 4 at the next stage, and so on. And their length, that is their p-Adic length, triadic length, is 1 over 3 to the k at the k stage. And you can start at 1 here, 1 to infinity, and you get, after summing this geometric series, you get 3 to the minus s over 1 minus 2 times 3 to the minus s. And as we know, that's valid, that this converges for real part of s greater than d, which in this case can be calculated. It's log 2 over log 3. I'll explain how this can be done in a second. And the Minkowski dimension. It's also the abscissa of convergence according to the theorem. In fact, this construction, this calculation tells you that the abscissa of convergence is exactly log 2 over log 3, because it tells you the infinimum of those alpha for which the series converges. Absolutely. It tells you exactly that. You can see very easily that the best real number for which this converges, I mean, s, real number s, is exactly log 2 over log 3. Now, since we know from the theorem that I mentioned that d equals sigma, d equals the abscissa of convergence, then we know the Minkowski dimension is also log 2 over log 3 in this case. Now, what are the complex dimensions? They are the poles of the meromorphic continuation of this zeta function. Now, this zeta function, this computation was valid only for real part of s greater than d. But then you can see that the end result, not the middle equality, but the end result is a meromorphic function in the whole complex plane. Therefore, this is the value of the zeta function, meromorphically continued to the whole complex plane. So here you have no ambiguity in defining the complex dimension. They're all visible. And all the complex dimensions are simply the poles of this meromorphic zeta function, I mean, this meromorphic function. Now, the numerator is never equal to 0. Therefore, the denominator is 0 if and only if 3 to the s equals 1, let's see, 3 to the s equals 2, which means s equals log 2 over log 3. So this is the meromorphic continuation valid for all s in C. And when you solve this equation, 3 to the s equals 2, you immediately find that the set of complex dimension is the set of d plus I and p, where p is called the oscillatory period of the ternary Cantor string or the p-Adic Cantor string, and it's 2 pi over log 3. And d is the Minkowski dimension, as we said, of the p-Adic Cantor string, but also it can be shown it's equal to the Minkowski dimension of the p-Adic Cantor set defined earlier. And this is an illustration of the complex dimensions. This is your oscillatory period, 2 pi over log 3. And this is a separation between these dots. These are the complex dimensions. D is log 2 over log 3 is about 0.6. And it's between 0 and 1, as we know from Benjamin theory. It turns out that for the Cantor set and the Cantor string, but in the Archimedean case, the complex dimensions are the same, and the geometric zeta function is the same as well. The ordinary Cantor string is simply the complement of the Cantor set, the ternary Cantor set in the interval 0, 1. Or if you want, is the disjoint union of all the middle third intervals obtained when you construct the usual Cantor set in the real life. Okay. So now let me talk about the p-Adic. Oh, I see that my time is coming up soon. So the p-Adic Cantor string. You know what? I'm going to skip that. Let me just say that in general, you have a p-Adic Cantor set, a p-Adic Cantor string, and it's a disjoint union of p-Adic intervals or balls. So you can write it this way. And there is one subtlety that I want to mention. So there is this notion of metric boundary of the Cantor string, of the, not just the Cantor string, but the p-Adic fractal string, is the union of the spheres. So the spheres are the set of points within a distance from the center equal to the radius of the ball. Now, we are in, now, okay. Now, So this is what I call the metric boundary. Now, the epsilon neighborhood of the metric boundary or of the fractal string, the thick inner epsilon neighborhood, is the set of points in the p-Adic string, LP, which are within a distance from the metric boundary less than epsilon. So it's the union of all these sets here. And all right. Now, okay, let me skip this a little bit, but this, and the volume of this thick epsilon neighborhood is just the Haar measure of that thick epsilon neighborhood. So as a lemma, this volume can be calculated explicitly as written here. And p to the nj, remember, is the length of your, is the radius of your, of the jth component of your string, of your p-Adic string. So this is calculated, it's a computation. And so notice that it depends only on these lengths, p to the minus nj, and not on the choice of the centers, aj of the ball. And that's the reason why the complex dimensions and the geometric zeta function will not depend also on the, oh, it's related to the fact that geometric zeta function does not depend on the choice of the p-Adic of the centers. All right. Now, if you have a sphere, okay, so the problem is, well, there's no real problem, but if you have a sphere in a p-Adic line, then it doesn't have zero measure. Unlike a sphere, say in R3, the surface of a two-dimensional sphere in R3 has measure 0, three-dimensional volume 0. But this is not the case here in the p-Adic case, as probably many of you are aware, and you can calculate it in terms of, okay, if the radius is not in p to the z, then the sphere is empty, and therefore the volume is 0. But if the radius of the sphere is in p to the z, then the radius is given by this, I mean, the volume of that sphere, or the length, the Haar measure, is given by that quantity here. So what you have to do in order not to have Minkowski dimension always equal to 1 for a fractal string, for a p-Adic fractal string, you just remove from the thick epsilon neighborhood the metric boundary. So the union, disjunct union of the spheres. And now you remove the, so now the true volume of the epsilon neighborhood is just given by the volume of this thin epsilon neighborhood once you remove the metric boundary. And so it's the difference of the volume of the thick epsilon neighborhood and the metric and the volume of this, of the boundary. So according to previous lemma, you can calculate it explicitly, and I'm not going to give it. Now, the main theorem is the following regarding complex dimensions, that we have an explicit fractal tube formula. Namely, if we have a suitable p-Adic fractal string, what is called languid, which roughly speaking is very precisely defined in the book and in the papers, but I don't want to go, it's too technical, into the details. But let me just say, roughly speaking, languidity means that the geometric zeta function grows polynomially along certain directions, vertical directions, or direction of what is called the screen, a suitable curve in the complex plane to the left of the vertical line, real part of s equals d, what is the Minkowski dimension. Let me leave it at that. Then for the assumptions. Then let me just say also that for self-similar string, in particular for the three-adic Cantor string, it's more than just languid, it's always strongly languid. And this will have a consequence in a second. So, also in the case of self-similar strings, p-Adic self-similar string, you always have complex dimensions of, in the whole complex plane, meaning the geometric zeta function has meromorphic continuation to the whole complex plane. Okay, So now the volume of the epsilon neighborhood, as I've defined it, is equal, can be written as a sum of residues of the geometric zeta function, or more precisely, that expression involving the geometric zeta function at the poles, meaning at the complex dimensions, more precisely at the visible complex dimensions. That is, those that are visible within the window. And then there may be an error term, and the error term can be estimated in terms of the screen. Let me not be too precise here, but it can be very precise. It's made very precise in the statement. Okay, so you can express the volume of epsilon neighborhoods, which are very important quantity in geometry, at least in fractal geometry, as a sum of residues of suitable functions here. And the residues are exactly at the complex dimensions. Now, in the case, the string is what is called strongly language, which is the case of all p-Adic self-similar string, particularly the three-adic Cantor string. Then you obtain what is called an exact fractal tube formula. You don't need an error term, and you can sum over all the complex dimensions. There is no error term in that case, but also if in addition, well, if we assume that the visible complex dimensions are all simple, that is, they are simple poles, then you have a much simpler expression. It's a special case of the previous theorem. It's a corollary. Is the sum of the residues of the zeta function divided by p times 1 minus omega at every pole omega. That is at every complex dimension, plus possibly an error term. But again, in the strongly languid case, in particular for all p-Adic self-similar string, you don't have this error term anymore. Okay, so I think I'm close to, maybe I should stop here. Let me just stop with that slide. That is, in the Archimedean case, there is a corresponding fractal tube formula. And let me just very, very briefly compare them. You have a 2 epsilon here to the power 1 minus s divided by s1 minus s times zeta L. In the non-Archimedean case, over QP, in other words, you have this expression that I've just mentioned. So the 2 here, and there is this difference, which I don't have time to explain, but the 2 at least I can explain, because the inner radius of the interval 0, 1 is actually 1/2, whereas it's 1 in ZP. All right, let me stop at this, and I will not talk about p-Adic self-similar string. That would be really a different talk, and the special case of the p-Adic, the fractal tube formula for p-Adic string. That will be for a different talk, but those who want to see the slides can see that part. It's in this second part of the talk. Thank you.
All right. Thank you very much for a wonderful talk.
Thank you.
Are there any questions for Michel? I will say this was very interesting to me. The talk that I'm going to give tomorrow very much uses the self-similarity in the p-Adics and analogs of the p-Adics in order to do some calculations.
Are you in QP or QP square or QB?
I mean, I'll be doing integrals over QP to the n, essentially, but using kind of the self-similarity in order to evaluate those integrals recursively.
I see. So unfortunately, tomorrow I have my lecture and my office hour, and then my PhD students' office hours. So what time is your talk?
Mine, I think, is 3 tomorrow, 2 o'clock or 3. But it will be on. Well, we will record it. All of these videos will be posted.
So I'll probably have to look at it because during my office hour for the PhD student. Okay.
So any further questions or comments for Professor Lapidus? All right. Well, seeing none, thank you very much. Very interesting. Okay. And yeah, look forward.
Okay, I'll stop sharing. Let me see if I can stop sharing this here. Oops. No. Stop sharing. Stop sharing.